All right, folks, today we are going to be learning our second factoring method. I want to remind you that when you see the word factor, that means to rewrite a polynomial as a multiplication problem. Method number one was to factor out a greatest common factor, which remember reverses the distributive property. So today we are going to focus on method number two, which is factoring a difference of two squares. Okay, now the first thing that we need to make sure that you can do is that you can recognize when something is a difference of two squares. Okay, um, so let's talk about how you're going to recognize that. Okay, to recognize a difference of two squares, these are the things that you need to be on the lookout for. First of all, does it have subtraction? And you know, the reason that we're going to want these things to have subtraction is because notice that the very first word in this is difference. And you all know that that's what a difference is. A difference is the answer to a subtraction problem. So if you want to know if something is a difference of two squares, the first thing you need to look for is, does it have subtraction? Okay. The second thing that we need to look for is it a binomial? Is it a binomial? Because notice it says that it's going to be a difference of two squares. So we want this thing to have two terms. Okay, and then the last thing you're going to look for is, are those two terms perfect squares? Are the terms perfect squares? Now, real quickly here, let's take a moment to review what we mean by perfect squares, because that's going to be kind of important here. A perfect square is the result of multiplying something by itself. So a perfect square is the result of multiplying something by itself. So for example here, 25 would be a perfect square because it is the result of multiplying 5 times 5, multiplying 5 times itself. X squared would be a perfect square because it's the result of multiplying x times itself. 9x to the fourth power would be a perfect square because that's the result of doing 3x squared times 3x squared. 3 times 3 would give us the 9, and x squared times x squared would give us x to the fourth. Something like 18, let me write it over here, would not be a perfect square because to get 18, I know I could do 1 times 18. I know I could do 2 times 9. I know I could do 3 times 6. But notice that in none of those multiplication problems that I've written am I multiplying something by itself. So this is not a perfect square. These over here are. So these are the things you need to check for to see if you actually have a difference of squares. I probably would check for this one first. Is it a binomial? Because if it's not, then there's no need to look any further. So does it have 2 terms? Does it have subtraction? And are the 2 terms perfect squares? So those are the 3 criteria that a problem would have to meet in order to be a difference of squares. All right, so now that we have that out of the way, the big thing that I want you to notice, or that I want you to know about this, is that to factor a difference of 2 squares, there is actually a pattern. So we're going to look at this difference of 2 squares pattern. All right, so here's how it's going to start. We're going to have a to the second power minus b to the second power. Now let's take a moment to check the 3 criteria for this problem. First of all, does it have 2 terms? Is it a binomial? Yes. Here's term 1, here's term 2. Does it have subtraction? Yes, right here in the middle. And then are these perfect squares? In other words, is each of these terms the result of multiplying something times itself? A to the second power is the result of a times a, multiplying a by itself, and b to the second power is the result of multiplying b times itself. So to answer that last question, are the 2 terms perfect squares? Look to see if you can find something that you can multiply times itself to get that result. So a squared minus b squared is a difference of squares. It meets all 3 of those criteria. Now, remember, to factor means to write a multiplication problem. So here that comes. The multiplication problem for a squared minus b squared is going to be a plus b times a minus b. So this is the pattern that you will always follow. When you see a squared minus b squared, you will write the multiplication problem a plus b times a minus b. Now, real quickly here, I want to point out that the a squared becomes an a times an a. The b squared becomes a b times a b. So that's how we're figuring out what to put in those parentheses. Now, to show you that this pattern will indeed work, let's take this multiplication problem and check it. So we know that to multiply, we would distribute. So if I do a times a, I get a squared. If I do a times a negative b, I get a negative ab. If I do b times a, I get a positive ab. Notice there I'm changing the order of the letters, and that's okay. And then b times negative b is a negative b squared. Now, combining like terms, I have a negative ab and a positive ab right here in the middle. Those two will cancel each other out, and I will be left with a squared minus b squared. So notice, this multiplication problem will take me back to what I started with. It'll take me back to a squared minus b squared. So this will be your pattern. 2 binomials. The a times the a comes from the a squared. The b times the b comes from the b squared. And then notice one of these is a plus and the other one is a minus. So that will always be your pattern. All right, so let's do some examples. So let's start out by factoring x squared minus 49. So first of all, let's check this to see if it is a difference of squares. Is it a binomial? Yes, there are two terms here, x squared and negative 49. Is there subtraction? Yes, I have a subtraction sign right here in the middle. And then is x squared a perfect square? Well, I know that x squared is the result of doing x times x. Is 49 a perfect square? Well, I know that 49 is 7 times 7. So both of those qualify as perfect squares because I can multiply x times itself to get x squared and 7 times itself to get 49. So now we will factor this. Remember, one of these will be a plus and the other will be a minus. Your x squared, it turns out, is x times x. Your 49, it turns out, is 7 times 7. So here is the multiplication problem that we would write for x squared minus 49. X plus 7 times x minus 7. And we could check this. If we do x times x, we would get x squared. If we do x times negative 7, we would get negative 7x. If we do 7 times x, we would get 7x. And if we do 7 times negative 7, we would get negative 49. The negative 7x and the positive 7x would cancel each other out, and x squared minus 49 would be my answer. And that checks. So notice how mentally I start by going through that list of 3 requirements and making sure that I truly do have a difference of squares. And when I find that I do, then I use my pattern. All right, so let's try this. Let's try 25x squared minus 4. All right, is this a difference of 2 squares? Well, first of all, is it a binomial? Yes, I have 25x squared and negative 4 as my 2 terms. Does it have subtraction? Yes. Are these perfect squares? Well, for 25x squared, is there something I can multiply times itself to get it? Sure, I can do 5x times itself and get that 25x squared. For 4, is there something I could multiply by itself to get it? 2 times 2. So because it is a difference of squares, I can do the pattern now, which will be 1 plus sign and 1 minus sign. The 25x squared breaks down into 5x times 5x, and the 4 breaks down into 2 times 2. So 5x plus 2 times 5x minus 2 would be my factored answer. That would be my multiplication problem. All right, let's try 9y to the 4th power minus 100. All right, let's go through the list. Is it a binomial? Yes, 2 terms. Does it have subtraction? Yes. Are these perfect squares? So think about 9y to the 4th. Is there something you could multiply times itself to get 9y to the 4th? Well, I know for 9 I can do 3 times 3. And I know for y to the 4th I can do y squared times y squared. So that's going to be 3y squared times 3y squared. And then for my 100, I can do 10 times 10. To be a perfect square, you have to be able to think of something that can be multiplied times itself to give that result. So now, time to factor this using my difference of 2 squares pattern. And I'm going to have a plus and a minus. The 9y to the 4th is going to give me 3y squared times 3y squared. The 100 is going to give me 10 times 10. And here would be my factored answer, 3y squared plus 10 times 3y squared minus 10. So notice, this doesn't take quite as much thought as the GCF method did. This is all a pattern, and if we can determine that it meets those three criteria, then factoring it ought to be pretty easy. All right, let's try this. Let's try x squared plus 81. Let's try factoring that. All right, so we're going to go through our checklist. We're going to go through our checklist and think about this thing. Is it a binomial? Sure it is, because we have 1, 2 terms. Does it contain subtraction? No, it contains addition. So when that happens, when I get to that second question and I say, is there subtraction in this thing? And my answer is no. What that means is this is not a difference of two squares. Not a difference of two squares because it doesn't have the subtraction that it requires. When that happens, what that means is you cannot use this pattern to factor it. And when you cannot factor something, the word you use to describe it is prime. And that does go back to something you already know about. You know, your prime numbers, the only way to get a prime number is from multiplying 1 times itself. So like, for example, 3 is a prime number because the only way to get it is 1 times 3. When I see x squared plus 81 and I realize that I can't factor it because it's not a difference of two squares, I say that it's prime. Because what that means is the only multiplication problem that I could write for this would be 1 times x squared plus 81. That would be the only multiplication problem I could write. So prime is the way we're going to describe that. So it really is important that you go through that list of three criteria first. And if the problem fails to meet any of those three criteria, then you cannot use this method on it. All right, let's try x squared plus, no, I don't want to do plus again. Let's try x squared. Oh, I forgot that does this. Let's just forget that. Let me just get a clean slide and start over. Let's do x squared minus 8. All right, first, let's go through our criteria. Is it a binomial? Sure it is. It's a binomial because it has 1, 2 terms. Does it have subtraction? Yes, absolutely. So we've met 2 criteria. Now we check the terms to see if they are perfect squares. So for x squared, can you think of something that you could multiply times itself to get x squared? And the answer is yes. I could do x times x, and that would produce the x squared. For the 8, same question. Is it a perfect square? Is there something you can multiply by itself to get 8? Well, to get an 8, I can do 1 times 8. That's not a number times itself. I could do 4 times 2. That's not a number times itself. So this is not a perfect square. This term is not a perfect square. So what that means is this is not a difference of two squares, and I can't use the pattern on it. So this one would also be prime because it is not a difference of two squares. So please, please, please make sure you go through those 3 criteria before you attempt to factor. Now, they can also make your life maybe a wee bit more difficult by just putting more stuff into the problem. So let's try factoring 64x squared minus 25y to the fourth. Let's go through our three criteria. Is it a binomial? Yes, two terms. Does it have subtraction? Yes, I can see that right there in the middle. Are these terms perfect squares? So when you see 64x squared, can you think of something you could multiply by itself to get 64x to the second power? I could do 8x multiplied by itself. That would give me 64x squared. Same thing for 25y to the fourth. Can you think of something you could multiply by itself to get that? Well, I could do 5y squared times 5y squared. So notice, you're probably picking up on this, but notice these exponents on these variables are going to have to be even numbers before you're going to be able to do this. All right, so this one meets all three criteria, which means we are going to be able to use this pattern to factor it. We're going to do 8x times 8x to get the 64x squared. We're going to do 5y squared times 5y squared to get the 25y to the fourth, and then always the pattern is one is a plus and the other is a minus. And by the way, it doesn't matter whether you put the plus first or the minus first, as long as you have one of each sign. All right, so when you're doing the problems today, do the same thing I did on every example first and go through your three criteria. If you find that it does meet all three and it is a difference of squares, then use the pattern to factor it. If you go through the three criteria and it fails any one of those, then it is not a difference of squares and it is prime. It cannot be factored. If you have questions about this method or anything that you need help with, please let me know.